Pienta, and I'm really excited to be here and talk about my latest research, VIGOR, and on behalf of Symantec Research Labs and my colleagues at the Georgia Tech Visualization Lab, specifically Polo Club, I'm going to introduce this new system we created to explore, summarize, and compare query results. So one of the things that really motivated this work is the growth of so many types of networks. And here we have a 10 million user, billion edge network of just computer gaming players. Right? There's over 800,000 gaming communities here. Maybe perhaps a more modest example would be this Rotten Tomatoes, which is a movie rating website network in which you have many actors, films, and directors all collaborating on different things with rich behavior. And so these sort of lead me down this road of why do we query graphs and what is this? Right? So we query graphs to detect, say, money laundering rings, right? Where you have some colluding bankers and business people working together in a sort of suspicious way to game the system. We query graphs to discover near bipartite cores, right? To get at the people who are trying to make their products look real when they really aren't. And to uncover fraudulent near-click reviews, right, on websites like Yelp or other review-driven websites. Right? And all of these have a common theme where you're looking for a particular pattern in a much larger network. Right? And so I'll now go through sort of a high-level overview of what the process of graph querying kind of looks like. So we'll start with our analyst, right, and they may be interested in a particular domain. In this case, we'll assume that they have a data graph, an underlying network. And in this graph, they have maybe millions of entities. Right? And in this case, I'm going to use films as an example, like this Rotten Tomatoes graph. Right? And the analyst here is looking for two co-directors of two films that star the same actor. So it's a very particular query they want to find. Right? And so what they can do through the sort of modern technology of graph databases and data mining is that they can find many results for this sort of high-level query. Right? And you could look at individual results like this particular one here, which is the Coen brothers, Oh Brother, Where Art Thou, and the Big Lebowski, all using John Goodman, or sort of connected to John Goodman. So there's, there may be many such examples, and a lot of these examples may share nodes, they may be distinct, they may be clustered in one particular area of the graph. And so it sort of raises a lot of challenges for our system. And so what we're doing in this work is really just focusing on the point at which you've gotten all of your results and how do we show them to you. And it turns out this is actually quite challenging because there's a few different problems here. One, you may have shared nodes and edges among your results. Right? And of course, your results themselves have nodes which have all sorts of different features. We may want to make use of those features to understand and compare them. And then of course, the third part is that all of your queries are arbitrary, so you may have any arbitrary subgraph, and many examples of it. This is compounded by the fact that sort of the industry standard right now is to give your results back as a list or a table. Right? And there's really little summarization done in these lists and tables. And one of the reasons why is that they really take a lot of comparisons. If you want to try to summarize it, you have to scroll along back and forth or up and down. And finally, it's unclear what's shared. Does one node come up only once, or is it in all of your results? And so in order to find that out, you have to constantly scroll back and forth. I don't think this is the right way to do it, and so we proposed VIGOR. And it's a solution to this problem. It's a visual interactive tool that allows you to summarize and compare your subgraph results. We make use of a new technique called feature-centric subgraph embedding, and we use that to create a similarity-based sort of 10,000-foot view to look at all of your results at once. Of course, we also still use multiple coordinated views. And then we tested this against Neo4j, one of the industry standards for a graph query. And we found that overall we're faster and less error. So, the main idea driving our 10,000-foot view is that we want to turn every match into a point, right? So you can imagine that each one of these squares is itself an entire subgraph, right? So here we have two examples with the Coen brothers and John Goodman, John Turturro. right? And then we can go a step further, and once we have these plotted, we can then cluster them based on their structure and their features. Ideally that they would be similar, right? And allow an analyst to come in and make semantically meaningful labels or generate new clusters by lasso. And so we actually implemented this, and here's the full system, VIGOR. On the top, you would enter first your written query, which is then pictured in the exemplar view. And so this will give you a force-directed layout showing you exactly what your query looks like. And then you can then click on any of these nodes and filter by specific values that it found in the solution set. Right? And so in the lower left conference, we've selected vast, and it will now only show us things for which vast was in that position in the solution set. And this fundamentally filters down the other views to make it easier to deal with the next view, the fusion graph. This is an induced subgraph of all of your results. And what that means is that we've taken all of the results and reduced them so that only one of each node exists, but then if a particular node exists in, say, many results, right, it will have many edges. So it will be very easy to spot if a node is in half the results, as it will be very high degree. This also allows you to look at node neighborhoods, as well as do customized layouts and some detailed information. The next thing, which is the high-level 10,000-foot view, is the subgraph embedding. And I'll talk a little bit more about how this works, but it gives you clustered concave hulls showing you different results and how they cluster together based on similarity using a custom subgraph embedding. And then you can select them, and you can select multiple of them, and it will show you on the right-hand side both the features continuously as a distribution and the individual values as a bar plot for however many clusters you select. So you can compare multiple and it will overlay them. Right? So naturally you'll ask, how do we go from all of these subgraph results to something that looks like this, where each result is a X and a Y? So I'll start off with, assume that we have some K results. For simplicity, we'll take just one of these results. And in this case, maybe we've got an author with a session, a paper, and a conference. Right? And we'll think about this in terms of the features of these nodes. Right? And so we know that every node will have some structural features because we can calculate those. We get to choose those, and we pre-calculate them one time before actually running the system. But then the features, the nodes themselves may also have semantically meaningful features from your dataset, right? And we want to make use of those because that may make the clusters much more meaningful, right? And so in this case, what we'll do is we'll look at, say, the author, right? So you have some structural features, each of these little blocks is a feature, and then the second part are the features that just belong to author. You wouldn't expect a session to maybe have the number of co-authors in it, and so you have a wide variety of features here, and some of your nodes may have none. Like the conference may have no special features and only structural features. And so what we're going to do is we're going to take these, right? And we know that we can get all of them for structural features. So every node will be guaranteed to have some structural features, but we know that some of these other nodes won't necessarily have features from your data set. We do have a solution for this problem because we do want to use them. Right? So what we'll do is we'll actually structure this in a slightly different way with subvectors. So we'll go across all of the nodes, and we'll take each of the clustering coefficients from that node, from your underlying network, right, and stack them up into a massive collection. And so then we'll take that clustering coefficient subvector, run it through some moment generating functions that will make it a fixed length. And what we'll do is we'll aggregate all of those for each feature into a massive array here. And we'll ravel that array into a signature. And this signature now represents our first result and all of its features, except it's in a high dimensional space. And so what we'll do is we'll take that high dimensional space and we'll repeat this process for every single subgraph result you have. And so now you have all of your subgraph results as points in a high dimensional space, and then we can make use of dimensionality reduction techniques to lower that to a meaningful subspace, and then take that meaningful subspace and spatially cluster it to give you some meaningful clusters. To test this out, we performed a within-subject user study with 12 people over the DBLP co-authorship network. And we had a series of tasks where we measured completion time and error rates. And here's just Neo4j's view, but I'll skip that for now. Here are 4 tasks. Specifically, what we did is we chose to give people the query because we didn't want to confound our timing numbers with the query creation time as well as the time to perform these essential tasks. And so what they would get is they would get the query, it would then be sent to the system, they would get the results back, and they would have to perform these simple tasks, right? Like in this case, looking for the author with the most distinct papers between co-authors who've authored at both InfoVis and KDD. The results of the study show that VIGOR is significantly faster and less error-prone than Neo4j, and you see this as a very positive sign. We also collected qualitative data, and again, people preferred VIGOR over Neo4j. And with that, finished.